Hello, so I want to focus on a project that we did for our algorithm analysis course, and this project was done by me and Musab, and we focused on implementing a paper from the Mathematical Programming Journal. The paper's title was A Nearly Optimal Randomized Algorithm for Explorable Heap Selection. So a very interesting name, a very interesting problem. And the authors of this paper, and I apologize for butchering the pronunciations, but the authors were Sander Bors, Daniel Dadouche, Sophie Huberts, and Danish Kashaev. And jumping into the problem itself, the question is, okay, we want to design a function called selectn, which is supposed to take in a potentially infinite binary heap and return the nth smallest element of this heap. So far, not a very complicated problem. You can just start picking out values and just store the n smallest values, but we're going to add a constraint on top of that you're only allowed to use logarithmic in n memory, so you can't store all n values. And on top of that, you can only do local queries. What that means, and a nice way to think about it, is let's say you're completely blind to this binary heap. You don't know what is inside this. In fact, you're starting at the root, so you can only see 1.1. Now from here, you can decide to explore by going either left or right. So let's say you go left. So now you can see this value 2.0, and if you want, you can remember that there was a 1.1 up here. You want to be careful about what you remember since you only have logarithmic memory. Now once you're at 2.0, next you can look at the value for 8.0 or 8.1. You cannot directly look at the value for 2.0 because for that you need to first go to 1.1 and then you can go here to this right value of 2.0. So the queries themselves have to be local, and this seems like a very extreme constraint, and a good question would be, why would you want to do this? And we can actually jump into why you want to do this. One possible case is integer linear programming. Integer linear programming is notoriously difficult because unlike linear programming, which has nice and optimal, nice ways to find optimal solutions and somewhat efficient, integer linear programming is NP hard. And since it's NP hard, you can actually use it to solve a wide variety of problems like 0-1 knapsack and graph coloring and traveling salesman problem. But it is NP hard, and so one way of solving integer linear programming problems is using the branch and bound method, which makes use of some linear programming and then also the same sort of heap idea that we were thinking about earlier. The solution space can be thought of as a heap, where at the root of the heap you don't have any sort of constraints, and so maybe the solution for that is just a linear programming solution. But as you go further down the tree, you add more and more constraints to your values, forcing them to be specific integers, and this helps you find the integer, the best possible integer solution. And the nice thing here about this setup is, as you're adding more and more constraints, the optimal value you can get actually reduces depending on the problem. Sometimes it will increase. If the goal is for maximization, the value that you can get at each of these nodes is going to reduce as you add more and more constraints, which means you end up with the heap property. And then you can start actually applying the explorable heap algorithm. And the local aspect is actually useful because sometimes doing queries at local nodes, you can have some overlapping computation because each of these nodes represents a linear programming problem. So solving neighboring linear programming problems might be more efficient than solving two completely unrelated problems. And the last thing to note is that, okay, we were talking about min heaps before. This is a max heap, and for that you just store negative values and things work out. So the idea still works. Now jumping into actually how you might want to solve this problem, one naive approach could be, okay, keep track of the smallest unexplored nodes you have so far in some sort of priority queue. So initially you only have the root, and the root is unexplored, so you explore its children, which is 7 and 12. Now of 7 and 12, 7 is smaller, so you explore its children first, so you get 10 and 15. Now from the current nodes, there's 10, 12, and 15. 10 is the smallest, so you explore its children, doesn't have any children, so you go to 12, then from 12 you go to 15 and 17, and this way you can recover the n smallest nodes. This takes n log n time because you're using a heap and you're doing n many operations on it, or order of n operations on it, but this takes order of n in space. So kind of expensive in the space, although pretty good on time. But what if we could still be good on time and not use as much space? And this is what this paper proposes. It's not the first paper to work on this. In fact, this was also worked on previously by Richard M. Karp, Michael E. Sachs, and Avi Wickerson. In fact, that is the original work. And note that Avi Wickerson is also the Turing Award recipient for 2023. The original paper is here. So they had some sort of solutions, and their randomized solution took only root log n space and gave a time complexity of n times exponential order of root log n. So kind of good, but this new proposed paper actually only takes logarithmic and n, so it takes a little bit more space. It takes logarithmic and n space, but it has a time complexity of n log cube n, which is really not that far from this n log n that we got with like none of the constraints. Here you didn't have locality, here you didn't have memory constraints, but here, despite that, you're getting a very fast algorithm. And the paper also goes on to provide a theoretical lower bound on the time that you would need, given that this much space, given that you have this much space. So that's why the paper is called nearly optimal. But yeah. All right. And so let's sort of dive into what the algorithm itself entails. And the way it sort of works is it depends on this notion of a good value. And so let's say I'm trying to find the the 8th smallest value of the heap. So this should be smallest. But a good value is something which is smaller than the 8th smallest value of the heap. How can I check if some value is a good value? And there's actually a nice way to do that. So let's say I talk about the value 4. And I want to check if it is a good value given that n equals to 8. Well, what I can do is I can start from the root of my heap. And I can see, okay, is it less than 4? Yes, it is. Okay, I will count that. Then I do DFS and I maybe go to the left child and I look at 2. Is 2 less than 4? Yes, it is. Okay, continue. Do DFS, go further down, look at 3. 3 is less than 4? Yep, cool. Go further down, go to 5. Is 5 less than 4? No, it is not. So we stop here. We go back up. We continue our DFS. Go right. 11 is still too big. Go back up, go back up, go right, go back up, go back up. And we can sort of count how many good values we can find, or how many values less than 4 or less than equals to 4 we can find. And this way we can find out if our given value was a good value or not. And the nice thing is, because of the heap property, we know anything further down that we can't see is also not good. Great. So that's one key aspect of the algorithm, checking if something is good using DFS. Now the important thing is the DFS has to be implemented in O of 1 space, which we actually messed up and did not do. But you can do that and then the algorithm works as intended. Another thing is that the algorithm focuses on expanding good subtrees. So first, I try to find if I want to find the 8 smallest elements, I first find the 2 smallest elements, then the 4 smallest elements, and then the 8 smallest elements. And one of the ways I find the 8 smallest elements is that, okay, if I know the 4 smallest, then I just need to find 4 more smallest from something right underneath of what I've explored. So maybe from 5 or from 11, 13, 17, 5.5, 4.5, from one of these places, I can continue downwards, okay? It's like I have to find some more nodes, so I continue downwards from one of these blue roots. From one of these randomly selected nodes, I continue downwards and I find more small values. And the values I will find here, since they're not considering values that occur at different parts of the tree, they don't give me exact answers, but they give me ranges. They can help me figure out what is the largest good value that I know of and what is the smallest bad value that I know of. And the idea is I keep exploring more and more subtrees until this range between the largest good value that I know of and the smallest bad value that I know of slowly converges. And once it does converge, then I know that I have found the largest good value, and the largest good value is the nth value itself. And yeah. And as we're sort of modifying these bounds on the largest good value, which is a lower bound for our answer, and the smallest bad value, which is an upper bound for our answer, that limits the possible places we'll actually explore further, because we need our further exploration to have one of those values. So I only explore from 5 because it does have a 7.5 or a 9.5. I explore for 5.5 not because of the 6.5, but because it has the numbers 8 or 8.5 or 9, something within this range. That helps me sort of filter where I can continue from, where it's even worth exploring from. Now the procedure, again, as we've roughly described, we start with the root, knowing that it's the smallest value, and we sort of try to double the set of smallest values that we have. And then we have this sub procedure called extend, which actually helps us continue from these different roots and expand outwards. And the goal is that, okay, at the end we'll get the nth smallest value and we can return that to the user. Now, the way the extend procedure works is a little bit long and a little bit complicated, so we'll break it down. In fact, let's break it down even more. Basically, what we're first going to do is when we want to expand outwards, we're going to randomly select a potential route to expand from. Now, note that the route that we expand from has to fall within sort of this range that we were talking about earlier. But this range is initially between 0 to infinity, not exactly 0. It would be between 8.3 to infinity. But we know that anything else that we find is going to be between 8.3 and infinity, so we're not worried about anything here. Our range is essentially infinite. So we just randomly pick one of these blue nodes. And one of these blue nodes becomes cyan, and we continue our exploration from there. And you see how the color is sort of swapping. Oops. You'll see how the color sort of swaps from 11.6 to 8.5, and that's because we've set it up so that the random selection is also done in order of one time. It's not just storing each of the blue nodes, it's just doing it more efficiently. Okay. Once you've done that, then from your root you check, okay, how many values in the actual tree are less than this value, and sort of we get 8.5, which has 5 values smaller than it. This helps us because 8.5 is larger than anything we've seen before, and we know it is a good value because we're trying to find, our n is 8, so we know since 8.5 has 5 nodes less than it, then 8.5 is a good value. Then we continue forward and we try to expand from this subtree. We try to find its 2 smallest nodes, and that gives us 13. And then we check how many values are less than 13. And we actually get quite a lot of values are less than 13. In fact, 9 values are less than 13. We had 5 less than 8.5 and 9 less than 13. So we have a range. We know 13 is a bad value and 8.5 is a good value. So we limit our range and then we continue. And we can sort of look at the algorithm as for run here. And we see how different roots are selected, and we check how many values are less than those specific selected roots. For example, I'm now trying to expand from here, so the hot pink represents that, okay, this is another call of extend, trying to increase the size of the subtree. And we're back here, we're trying to find the second smallest value in this subtree. We get 13. We check how many values are less than 13. It's quite a lot. Then we need to find a new root between 8.5 and 13. So we selected, I think, 11.6 first, and then so on. And we continue exploring. Try to find the second smallest of this tree. We get 12.6, but that's kind of large. We end up with more than 8 nodes. So then we try to find a new root. We get 11.6 as a root. We see how many values are less than that. It's exactly 8. And we can stop. And so that's how the algorithm works. And just going roughly over some of the implementation details and some of the enhancements that we made as part of our project was firstly, actually implementing it. And when we also tested the algorithm to make sure it works. And we tested it both on actual explicit heaps, so heaps with literally the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in order, and then also heaps with some random values obeying the heap property. We got correctness in both of these, evaluated against best first. We also used it to solve knapsack. The original algorithm also did not work for duplicate values, so we added an extension to work for that. For some duplicate, it won't work for very heavily duplicated values, but it will handle some bare minimum duplication. On top of that, the original paper only has high-level descriptions, no pseudocode, so the code did take some effort. And there was a slight error in the good values function, so we added our own modification there, and we got that verified from actually the paper authors themselves, and they were like, yeah, this works. So that's that. And some of those details are also in our report, which is in our GitHub repository, and I'll show it in a minute. On top of that, again, we used this implementation to actually test the branch and bound method to see if it actually works. And again, the visualization we created is new, and the empirical testing we carried out is new. And again, we tested on some explicit heaps and some implicit heaps. For the explicit ones, we compared against best first, and then for the implicit ones, we checked using the pulp library, which has an integer linear programming solver, to just validate that the answers we're getting are the same that their solver is getting. We also did some, and so the this actually worked. Yes, it worked. And then we did some complexity analysis, seeing how the performance scaled with the value of n, with the number of nodes, or the nth value. Yeah. And we found, actually interestingly, that if you normalize it with n log n square, it sort of actually levels out, whereas the paper proposed that it's n log n cube. Now this could hint towards, oh, maybe we should carry out further analysis to find out if it actually is n log square n, because that is possible. Although another possibility is that we just haven't found the worst case inputs for this, and that's why the complexity that we're getting is better than what we'd expect. But definitely for n log n cube, we do see that the curve levels out and in fact decreases. And lastly, we also compared against best first, and we saw the time difference there. And yes, the algorithm took a bit longer, but not too much longer. Note that this is a logarithmic scale, so like some of the growth is being missed out here, but yeah. And as for future directions, for anyone that might be interested in taking this project forward, one thing is maybe doing some memory usage analysis to actually show that, oh, in fact, this is only using logarithmic in n space. Another thing is that for that to work, you have to make the DFS a bit more memory efficient. On top of that, our heaps are not too suitable. If like the whole heap is the same value, it will sort of blow up there. So you can add fixes for that. And again, you can also update the visualization, perhaps by showing the current lower and upper bounds that we have, so that can aid sort of understanding. But that sort of covers the actual presentation in itself. Here are some of the references we have, and thank you for listening. But before I end, here's also the actual paper itself that was the reference for this whole project. It is a very interesting paper, very beautiful diagrams, and yeah. And there's also our actual report, which is part of our code repository, so you can find it there, and has a bit more details on a more intuitive understanding of the algorithm, how exactly we went about implementing and testing all of these, and some of our testing results, and just our general reflections. But yeah, so thank you for sort of listening, and I know it was very extensive, but I hope it was interesting. Yeah, take care, bye.